let's just take a look at what we've seen so far over the past chapter. We have Ampere's law, which relates this curly pattern of magnetic field to current enclosed by a circular loop. Okay. We also have had Gauss's law, which relates the pattern of electric field over an area, or the electric flux over a closed surface, to the charge enclosed. We've had the magnetic version of Gauss's law, which relates B dot n hat dA, the magnetic flux over a closed surface, to, well, since there aren't any magnetic monopoles, then we said the net magnetic flux over a closed surface should be 0. And so we have three relationships here, two of which have to do with area. One has to do with a path integral over a length. And the area ones have electric and magnetic fields, and this one just has magnetic fields. So by symmetry, we might think that there's got to be a relationship of E dot dl over a closed path, a closed loop. And in fact, we've seen that before, right? We talked about this a little bit last time. If you're doing the path integral of the electric field, you are finding what? Potential difference, right? And we said that if you take the round trip potential difference over a closed loop, you should get what? You should get 0. Well, this is true for cases where the electric field is created by static charges. Okay? Now, you might say, well, what else is there? What else can create electric fields? Well, we're actually going to see today that there is another way to generate an electric field, or another way you can put it is a different type of electric field that's not associated with charges, but actually associated with changes in magnetic fields. And that relationship is going to be called Faraday's Law, but I just want to introduce this here with a little demo. Here, this is a coil of wire. Okay, it's just copper wire wound around 3,400 times. And I'm going to plug this copper wire into a galvanometer. Now, a galvanometer is just basically a voltmeter, or you can use it as a voltmeter or an ammeter. It's just going to detect if there is a current running through the coil, and right now it's reading 0, okay, meaning there's no current. If current flows in one direction, the needle will deflect one way. If it flows the other direction, the needle will deflect the other. Okay, so it's just measuring a current through here. And let me project this on the screen here. See if we can all see this. And let me rearrange this here. So we've got our galvanometer hooked up to the coil, and it's not hooked up to any power supply, so obviously there's no current running through. All right, so I have a bar magnet. Okay, so North Pole here, South Pole here, and the bar magnet, of course, creates a dipole pattern of magnetic field. So I'm going to bring the bar magnet near this coil. What just happened? So just move this out of the way for a second. All I'm doing is moving a bar magnet near this coil, and then I'll just sit it here. And it looks like if it's just sitting here, nothing's happening. I move it away, at least for some time. What happened to the coil? There was a current. Okay, if we believe what the galvanometer is telling us, there must be a current in here, right? The needle is deflecting, measuring a slight current throughout these 3,400 turns of copper wire. Now, there's something interesting going on here. We have a magnetic field, right? And a magnetic field is being produced everywhere in space, including at the location of the coil. So this is the North Pole. This is the North Pole. So I bring the North Pole nearby, and it's making a magnetic field here pointing in that direction, right? If I bring the North Pole closer, what happens to the magnetic field at the observation location of the coil? It gets bigger, okay? If I bring it away, what happens to the magnetic field? It's smaller, okay? So the magnitude is changing, right? If I just keep it here, there's a magnetic field here, but it's not changing. So apparently, this current has something to do with a changing magnetic field. And if I flip the direction, if I move the North Pole closer, you can see the needle deflect in one direction, and it deflects in the other when I move it farther away. And then if I change the direction of the field by moving the South Pole closer, you see the deflection is exactly the opposite. So here's moving the North Pole closer, North Pole farther away, South Pole closer, South Pole farther away. So there's something here having to do with a changing magnetic field. And it's producing a current, and if there's a current in the wire, meaning the charges are moving in the wire, what do we have to have in the wire? Moving electrons, which are driven by what? But a potential difference, okay, not a magnetic field, because a magnetic field can't cause a charge to accelerate, it can cause it to change direction, right? If a magnetic field, let's look at that. Bring the lights up here. A magnetic field, we know, on a single moving charge, if you have a magnetic field, say, pointing in this direction, well, if the charges aren't moving to begin with, we have a velocity, say, equal to 0. So let's say we're looking at the initial state here. The magnetic force is QV cross B, right? And so if there is no velocity, then there's not going to be a magnetic force. So we can't actually get a magnetic field to cause the charges to move. So instead we need what? An electric field, right? Someone said a potential difference, but behind a potential difference we have an electric field. Because electric forces can drive charges. Electric forces are Q times E, and so as long as you have an electric field, you can get the force to accelerate the charge in that direction or in the opposite direction if we're talking about negative charges. So somehow there's an electric field associated with a magnetic field that's changing. And you might say, well, it doesn't have anything to do with, we've seen motional EMF, right? So maybe somehow this is a motional EMF effect because the bar magnet is actually moving. Well, there's another way we can create magnetic fields, which is we can have another coil, right? If I run a current through this coil, I can make a magnetic field. So here's a coil connected to a power supply. Well, it's actually not that high voltage. I think it's only 20 volts, but it's pretty high current. Right now it's turned off. So I'm going to bring this second coil near this first one. Now, if I run a conventional current through here, and I'm not sure what the direction is, I think the conventional current, the way it's hooked up, would run that way. This also is going to create a magnetic field, right? So if the conventional current's running that way, it should make a magnetic field pointing in that direction at this observation location, the observation location of the original coil. Well, right now the power is turned off, so there's no magnetic field, but I'm going to cause that to change by switching the power on. If I do that, what happened? Try it again. So here I'm turning it off, and it deflects a little bit. Turn it on. Maybe you need to kill the lights. Well, I think we can see the needle. Let me move it down a little bit. Better. Do that, and the needle deflected for just a fraction of a second. Well, consider, okay, so we said that it was associated with a changing magnetic field. So what's happening when I throw the switch? Okay, we're generating magnetic field into this coil, right? There's some initial transient. Right now, the magnetic field is what? If I have the power turned off, the magnetic field is 0. I turn the power on, and the magnetic field goes from 0 to something, okay? During that brief transient period, and that transient's kind of slowed down when I turn it off, but when I turn it on, it's pretty quick transient. During that brief transient period, the magnetic field created by this coil, the one on the left side, well, my left, your right. The magnetic field on your right suddenly goes from 0 to something, right? And so there is a changing magnetic field here for that brief amount of time, okay? So again, something having to do with a change in the magnetic field and is creating, or maybe creating is not the right word, but it's associated with an electric field, okay?